Because they used to not be right, it was creepy. But yeah, it's an actual show. They did. Because I want to do it. That's what I really makes.
Okay. Like I said, we're going to start over since I forgot to tape the first two questions. Alright. Shh. A microscopic magnetic region composed of a group of atoms whose magnetic fields are aligned in a common direction is called a domain. And then if they're not aligned, they will show no magnetism. The no, two no's is not necessary, however. Okay. Number 2, the current in a long straight wire produces a magnetic field. These magnetic field lines do what? Form circles that go around the wire. You guys are amazing. Thank you, Michael. Okay. Number 3. A solenoid is in an upright position on a tail. Remember, a solenoid is a coil of wire that a current runs through to generate a magnetic field. When viewed from above, this causes the solenoid to have a blank magnetic pole at its bottom end. Let's figure that one out first. Okay, so if we have a solenoid sitting on a table, it's going to be a coil of wire like that. You can draw on the table, and we're looking at it from the top, and it's going, say clockwise or counterclockwise? Clockwise. The current's going like that. So what we want to do is use our right hand rule with the curved fingers to figure out what it's doing in the middle of the solenoid. So there's a magnetic field going up or down in the middle of the solenoid. Into the board or out of the board? Down. So it's going to be going down, in. So like if we drew our magnetic field, it'd be going like that through the center. Does that make sense to everybody? Okay. So you understand that like the magnetic field is going to be putting down on the inside of the wire everywhere? Like no matter which way you put your hand here, it's putting in.
Yes.
And it's going to be putting out on the outside.
Correct.
So the magnetic field is going to be going around like that.
Oh,
Does that make sense?
Yeah.
No.
You get it, Kyle?
No.
Okay. So going into the board there, and everywhere, like on the inside, no matter what way I put my hand, it's always pointing down in the middle. On the outside, it's pointing up everywhere. Does that make sense? Okay. So now, so it's coming out of the bottom and into the top. Is the north pole of a magnet where the magnetic field comes out of, or goes into? Out of.
No.
Magnetic field lines go out of the north pole into the south.
Oh. North is up. Since one is.
What?
Why is south one?
Okay. Shh. So magnetic field lines go out of the north pole of a magnet and into the south pole of a magnet.
Always?
Always. So where in a solenoid, wherever the magnetic field comes out of, that behaves like the north pole. Wherever it goes into, that behaves like the south pole. Okay, so the first question on here is, causes the solenoid to have a blank magnetic pole at its bottom end. So it is a north or a south pole at its bottom end?
North.
North. So that eliminates 2 of the answers. And if we took a compass and we had the north pole of the magnet, would that be attracted or repelled from the top of the... Attracted. So what's the answer? A.
How do you know that it's attracted?
Because it says if you bring a north pole of a magnet toward the top end we said is a south pole.
Oh, okay.
So it's north and south and it's going to attract. Does that make sense, everyone?
Yeah.
Yeah. So again, the answer is A. Okay. When an iron rod is inserted into a solenoid center, the magnetic field produced by the current in the loops causes the iron to return to an unmagnetized state. Does that one make any sense? No. Forces the domain of the iron out of alignment. So you think it makes the iron magnetic or non-magnetic if you put it in a solenoid like this? Magnetic, so B doesn't make any sense either. Causes random orientation of the domains in the iron? Nope. And causes alignments of the domains in the iron. So that would make the iron magnetic, so that would make sense. So D. Alright, number 5, this one's just like when we kind of just went over number 2. The lines of magnetic field are on a current carrying wire. Which one is it? Point away from the wire, point toward the wire, form concentric circles around the wire, or are parallel to the wire?
C.
C, form concentric circles around the wire. Alright. Consider two long, straight, parallel wires, each carrying a current I. If the currents move in opposite directions, do the wires attract or repel?
Attract.
If they move in opposite directions,
They repel.
they repel. So it's kind of, and this gets confusing. In this case, it's the same direction attracts, opposite directions repel. So number 6, the answer is B. Alright, number 7, this time the two wires are carrying current in the same direction. What are they going to do?
Attract.
Attract. So number 7 is A. Right. Number 8. All the following are ways to induce an EMF, and remember EMF means voltage, in a loop of wire except which one. So we need to figure out which one of these is not going to change the magnetic field or the magnetic flux going through the loop of wire. So if you move the loop into or out of the magnetic field, is that going to cause voltage?
Yes.
Yes, so the flux is going to change in that case. If you rotate it in a magnetic field, yes, it will cause a change in flux because the flux is the amount going through the center of the loop. So if you rotate it, the size of the loop keeps shrinking, so the flux is going to shrink. Does that make sense, everybody? Alright, move the loop parallel to the magnetic field. No, that's not going to change the flux. If it's pointing this way and you move it this way, if it goes parallel to the magnetic field, the magnetic field lines through it stay the same. And if you insert it into a change of magnetic field, that's going to change the flux as well. Does everybody understand that one? Okay. Alright, number 9 and 10 are both math problems I didn't really intend to put on there, but they have the same equation. For both of those, it's V equals negative N, change in I over T. The one thing I do want to point out for both of those is that for 9, yeah, for 9, the equation ends up being V equals negative N. Since flux is A times B, in number 9 the area stays the same and the magnetic field changes over T. And because it just gives us the magnetic field, the change in the magnetic field in number 9. Does everybody see that? It says the magnetic field increases by 0.65 Teslas. So we just have to put 0.65 in for the change in B there. Do you guys want to try to work it out now? See if you get through an answer, or
Yeah. No.
right, so I want to tell you the answer for it, and you can work it out later if you want and have it after we're done, and if you have questions you can ask. So the answer to number 9 is A, and the answer to number 10 is A as well. Oh, I'm sorry, the answer to number 9 is D, not A. Alright, number 11, the operation of the electric motor depends on, it is not the Doppler effect. Not that one either. C. It is the magnetic force acting on a current carrying wire in a magnetic field is what electric motor depends on. That's because electric motor has two magnets and you run a current through a wire, and those two magnets cause that wire to move around in a circle. Alright, and just so you guys know, the Doppler effect is a
Yeah, it's what Sheldon wears now.
Yeah, it's what Sheldon dresses up as on Halloween.
We'll talk about that in the next chapter.
Really?
Yep.
We're gonna watch that episode?
Yep. Okay. Number 12. Which conversion process is the basic function of electric motor? So what does electric motor convert from in terms of energy?
Mechanical to electric.
It is B. Electric motor converts electrical energy going into the motor into mechanical energy in the motor turning. Does that make sense, everybody? And a generator is the opposite of that. A generator converts mechanical to electric. Alright. Changing the magnetic field intensity in a loop of wire, in a closed loop of wire, induces. What does it induce? Current, voltage, or both, or neither? Both. Okay, 14 is the name of something we didn't really talk about. Well, we talked about it, but we didn't talk about the name of it. Okay, phenomenon by inducing voltage by changing the magnetic field around a conductor is called electromagnetic induction.
Oh. Actually, what?
Huh?
I was gonna guess A. Yeah, no, it was.
Okay. 15 is kind of a strange question. A generator is used to light the light bulb. Energy for lighting the light bulb actually comes from, like, the first place it comes from is the mechanical energy or mechanical impulse to the generator. So B is the answer you're looking for there. I mean, you could also say it's going, if you went back further, it's from a dead animal, if it was oil or gas. The sun would be is almost always the answer, except unless it's geothermal.
The Big Bang.
The Big Bang? Yes, they did come from the Big Bang. All energy originated there. Alright. Number 16. A device that transforms electrical energy to mechanical energy is a?
None of the above. D.
D. Is the same question as before except reversed. If it was mechanical to electrical, then it would be a generator. Does that make sense? Okay. 17. The principal reason voltage is induced in loops of a generator coil is that the loops are rotating, change the amount of magnetic field within the loops?
D.
Yep.
It's E.
It is not E.
It's D.
It is A. The loops of wire rotate, and that changes the amount of magnetic field within the loops. It is not always all the above, Michael.
Just wait till the test.
It's true, false in the test anyway.
Exactly. It has to be all the above.
I guess for true or false, it would be all the above or none of the above each time. You can split it that way. Alright. Number 18. A device that uses two coils around an iron core to change the voltage across the circuit is called a transformer. Okay. Number 19. A step-up transformer. Does it increase, decrease, or do nothing to the voltage? Increase. Step-up transformer increases voltage. Step-down transformer decreases voltage. Okay. Which of the following statements about a magnetic field lines around a permanent magnet is true, except which one?
B.
Did you actually read any of them, Brian?
Actually, no, that's the problem is
Okay. It is A. Magnetic field lines actually appear to end at the south pole of the magnet. They come from the north pole of the magnet.
Oh, yeah. Literally.
Alright. Number 21. Which compass needle orientation in the figure above might correctly describe a magnetic field at that point? Remember, they come out of the north and go into the south.
So A.
A.
Like 5.
Alright, number 22. In a magnetized substance, the domains C line up in one direction. If it's magnetized, they line up in one direction. If it is unmagnetized, they're randomly oriented.
That's what I was thinking.
An unmagnetized substance. Right. In a permanent magnet, yep, all domains persist after the external magnetic field is removed. In soft magnetic materials, which means magnetic materials that can be like attracted to a magnet but aren't magnets themselves, what happens to when an external magnetic field is removed?
D.
D. It turns to its unmagnetized state.
I was thinking 1 step ahead.
Good job, Michael. Alright. According to the right-hand rule, if a current-carrying wire is grasped in the right hand with the thumb in the direction of the current, the 4 fingers will curl in the direction of the B, magnetic field. Any questions about any of those guys? Do you feel like you could answer all these reasonably well, even without me?
I'm thankful for your help.